speaker is Professor Misha Pavel. He is now in the director of the NSF, and the project called the Smart Health Wellbeing the Smart Health and Wellbeing. So this is the first project for the NSF, not NIH, and for thinking about kind of health informatics. He is now also professor of the Oregon Health Health Science Universities, and he is one of the leading person in this country for working about the health informatics. And his talk today is the transforming healthcare with biomedical engineering model-based approach. Misha, please.
Good afternoon, and thank you for inviting me up here. And I'm going to actually give a talk with several parts, and I have to move rather fast because I have a load of slides, even though my wife warned me not to do that. She's always right. I will talk a little bit about the NSF, then about the particular program, and then some of the challenges that we face as we go on. And my emphasis, as you will see, is focusing on modeling, computational modeling. So NSF is a federal agency that was established in 1950 with the notion of promoting basic science, and this is what NSF has been doing for many years. In addition to supporting research, we are also focusing on education and future needs for the society. Our budget is about $7 billion, and we process about 440,000 proposals per year. And as you know, we use evaluators, panelists that we draw from communities like this one. The NSF proposals are evaluated on two aspects: intellectual merit and broader impacts. And I will discuss this a little bit later. As I mentioned before, we also really emphasize educational aspects as well as societal advances. Now, NSF has a number of directorates that range from geosciences to computer science to physics and mathematics. We have a bunch of cross-cutting programs, and then offices that support the work. I'm located in computer science and engineering, SCIENCE, that consists of 3 divisions, and and my program is located in the Division of Information Intelligence Systems. That division, actually headed by Howard Wacklar, is focused on 3 components, and Howard likes to think of it in 3 dimensions. When those of you who are engineers, you know the right-hand rule: if you take information and move it into computing, you get people. And so our division is then, everything that we do is focused on people, including those programs that do not have obvious relationship to people, like robot intelligence, information integration, and of course human-centered computing does. And my focus during this presentation, especially the later part, will be on behavioral aspects, since so much of this conference is focused on devices and physiological measurements. Now, one of the big changes that stimulated our most recent programs has to do with the fact that we can now observe lots more than we used to be able to, and that those observations give us what we call big data. And I'd like to mention to you that there is a program in big data that goes across agencies. I don't know why this went ahead. Oops. doesn't seem to go back. Okay. The big data is a program that actually is cross agencies, includes NIH, NSF, and NASA and other agencies. Now, let me talk a little bit about the Smart Health and Wellbeing program. It was stimulated by the fact that healthcare is in crisis, and we all know that. We're spending too much money, and our results are not great. One thing I want to point out, this group is particularly attuned to this, so I don't go through details, but the last sentence here, the 3 lifestyle behaviors are responsible for actually 40% of premature death. And I think this is very important to remember as we go on. Now, this is just a graph that shows how US is spending much more than most countries, in fact, twice as much as any other country per capita, as well as percentage of the gross domestic product. And yet the results are kind of mediocre. This has been recognized over the last few years by a number of organizations. This particular reports that I'm having, that I presented here, are produced by the President's Council of Advisors for Science and Technology. They produced 2 reports in 2010, and if you haven't read them, it's useful, and especially, actually both of them are very useful to understand, because it will tell us where the thinkers that are the visionaries are thinking we're going. And in addition to that, there are a number of NRC reports that address the same issues of healthcare. Now, they all agree that healthcare has to be transformed. And I'm going to go fast through this because you heard from Eric Toppel earlier this afternoon, or this morning actually. And we completely agreed we could actually exchange some slides. It's clear that medicine has to be transformed from episodic and reactive to proactive and preventive. It has to be transformed from hospital-centric and to patient-centric. In fact, I think that the hospitals were designed actually by a workshop of bacteria. They all got together and said, well, how could we design a system which brings people who have already compromised immune system together and exchange to each other? And that's what hospitals are, waiting rooms and so on and so forth. Currently, when you go to clinician, the decision, both the diagnostic and therapeutic decision, is based on the experience and training rather than all the available data. In fact, the director of National Library of Medicine says that if in his area, he's a pathologist, he would go home and read 2 articles a day. In 1 year, he would be 480 years behind. So clearly, we need something better than what we have now. The current system is so fragmented, and you know better than anybody else. And finally, currently, our patients are mostly naive and passive, and they have to be empowered and participate in their cure. Now, changing behaviors is hard, especially when we face this kind of stimuli. And this is another version of that. Even though we know what the right answer here is, we still probably go for the bacon. This is the sort of a schematic view of the version of future healthcare that is based on continuous monitoring on the right side of activities, physiological, and other contextual variables that were important in health. Then on the left side, it's the intervention. And intervention doesn't mean necessarily only intervention when you're sick. but a proactive care, which includes self-care as well as devices. And this infrastructure that's needed to do this is one of the key problems. And this kind of vision then motivated the development of the Smart Health and Wellbeing program. The Smart Health and Wellbeing program is thought to have three kind of areas. These are not mutually exclusive. These are overlapping, obviously, but I give you some picture about where we expect the technology, and especially computer science and engineering, can make impact on healthcare. First, there is need to build infrastructure, and by infrastructure and the ideas that underlie infrastructure are enabling universal language that would enable us to harmonize all the data from different EHRs, from different electronic health records, to be able to talk to each other. Non-trivial problem. Data to knowledge and decision has to do with the ability to go and bring all the data that's available from randomized control trials to laboratory to individual patients and EHRs at the point of care. The empowering patients I already mentioned before, and finally, systems and devices that both do sensing and intervention are going to be a huge component of the future medicine. Again, this is so resonating with what Eric was talking earlier. The current version of the Smart Health and Wellbeing program is across 3 directorates: engineering, science, and SBE. And the important part that you need to know is that though one has to choose an important problem in healthcare, something that's really going to have impact on healthcare, but at the same time, we need to, the proposals that would be funded have to make advances in fundamental science in one of the 3 directorates. These are examples of funded proposals that range from systems analysis and signal analysis, pattern recognition, inference activities, robotics, all the way to social computing and monitoring and home care. And again, I'll be happy to talk to you about the details if you're interested. Just don't hesitate to send me email. The proposals are reviewed on 3 criteria. As I mentioned, intellectual merit, broader impacts, and particular requirements of the Smart Health and Wellbeing program. The intellectual merit essentially have to do with how important, how transformative the idea is. And here I wanted to emphasize that we're looking for innovation. We are really giving instructions to our panelists to really focus on what is the transformative idea in the proposal that's being judged. And that all our program directors are focused on that, and that's very important. And we generally, even if everything is great about the proposal, if it doesn't have that important intellectual contribution that's generalizable beyond the particular application, it won't get funded. And of course, we have the standard evaluation criteria and broader impacts and so on, which you are familiar with. It has to be of social import, and if you're addressing the issue of smart health, you'll have that. The smart health and well-being requirements are, again, standard. They include collaboration plan, and that's very important. Usually, we almost require people having clinicians and engineers work together. But I would like to also point out that data management now is extended to software in addition to the data. And that is going to be, that is being judged as well as the other aspects of the proposal. Next year, however, I was hoping that and we're still working very hard to be able to actually come up with a joint solicitation between NIH and NSF. All right, so this ends my part about my part that I wear my NSF hat, and you notice this sort of qualification that from now on, it's not necessarily NSF opinions, but my own as a professor at Oregon Health and Science University. Although I must say that proposals that include modeling are likely to be more generalized, more likely to be transformative and generalized to other areas, so they are more likely to be funded. I'm going to start with how do you select a problem? Well, unfortunately, many proposals that we got this year had this trajectory. The PI invented a hammer, then looked for nail, and then wrote a proposal how important that nail is to the country. But that's often transparent. And sometimes it works, but often it's not really addressing the important problem. A much better approach is to really find clinical application that's really important, figure out what the potential solution is, get innovation there, and then do the proposal. Now, choosing problem is not easy, and I don't know how many are familiar with the Pastor Quadrant. It was written by Donald Stokes 10 years ago. But the idea is that projects are generally can be assigned to be motivated by applications or by pure understanding, pure basic science. So, for example, Niels Bohr was motivated by pure science. He couldn't care about applications of his models. On the other hand, Edison was actually discouraging people from trying to figure out why certain filaments work. He just wanted to find filaments that wouldn't burn out. Pasteur, on the other hand, was motivated by both. He was trying to figure out the farmer's problem and why the milk spoiled and why the wine spoiled. But at the same time, he was trying to understand what the underlying science was. And of course, we can upgrade to Steve Jobs, who also was not very much into science, but rather. And then there is another quadrant that is more of a common man kind of quadrant. Now, when you're choosing a problem, it's important to see how important that problem. So, for example, obesity is an increasing epidemic. And if we don't do something about it, it's going to really hit us hard. The same thing is with aging. This is a dependency ratio, retired to working people. And what you see here is this rapid rise that's due to baby boomers. And baby boomers are very dangerous people. I'm one of them. We are going to make a lot of trouble because we are very selfish and we don't take no for an answer. And if we are not taken care of, well, you'll know about it. So young people, watch out. And we call this Silver Tsunami because of the kind of impact that may have. Now, as I mentioned, solving these problems, you need multidisciplinary or transdisciplinary teams. And that means each member should actually learn the language and even culture of the other collaborators. And if you don't have that, you actually are likely to go astray. To create these teams is very difficult because there's no cross-disciplinary recognition. I remember the chair of my department, and at one point, famous engineer from Bell Labs and Intel, went up to the hill to the medical school and said, I am John so-and-so. And they said, okay. And he came back totally disappointed and never wanted to do anything with medical domain. But they didn't know. So don't expect the recognition to transfer across discipline. Now, how do you know that you succeed? Well, one good test is that if you ask your engineer that solves the problem, is trying to solve the problem is, well, what's the underlying reason for your solution or for the phenomena? And when they answer, well, I'm an engineer, you have to ask the clinician. That's the wrong answer. Everybody on the team has to know. The other way to know is that everybody has to laugh at the same jokes. And of course, the engineers like these Dilbert jokes. This particular one has to do with the cloud computing and platform, and it's just overused terms. And engineers understand that one, and typically clinicians and biologists understand the one that has to do with brainstem storming. Now, how do we recognize innovation? That's very hard. And this is a little story about sailing ships during the 19th century. There was a lot of research on improving sailing ships, and they incredible results in the first half of the century, smaller results later. And this is one of the latest designs. But as they were sitting in the harbor in England, there were these steam machines. And of course, everybody knew that you couldn't build a steam ship that would be capable of going across the Atlantic because it would take too much coal. Well, within 5 years, the sailing ships were gone. So here is that you went from the cut, but not from your team players. And of course, recognizing innovative solutions is very difficult, as we heard yesterday from William Brody. And you have to force yourself, and especially if you're experts, you are too used to knowing what works or what doesn't work. Suspend that. And of course, this is what you often face. Change is very difficult. This paragraph was written about an instrument that will never work, of course. And does anybody know what the instrument is? It was something that Eric Topol mentioned that's being slowly phased out. It's the stethoscope. And it was used for many, many years satisfactorily until recently. So here is a cartoon. I'll be happy to give you innovative thinking. What are the guidelines? Yes. Mobile health, I'm not going to talk about because Eric spent so much time on that. And but here are data that we're collecting in Oregon from homes. And these data are collected with a very cheap system consisting of passive infrared. Passive infrared will be slightly modified by reducing the angle of the visual angle so that we can measure narrower regions for speed measurement. Computers, contact switches that are on the doors and refrigerators, and so on. These are the real data from one subject. This is only 1 year. The time and year, the day is along the periphery of the circle. So each circle is a day, and the day 0 starts here, and 1 year is over here. This is midnight, so you can see this quarter is night, and the different colors are the different sensor events. So you notice the first half a year this person slept well, then somewhat less well. This person prepared dinner or breakfast, lunch and dinner in their kitchen. But very rarely did this person go out. This one lives in a retirement community as opposed to prior one that lived in home. And this one actually gets out every day for breakfast, lunch, and dinner. And as a result of that, they may be more socialized, and the socialization is extremely important. But this kind of visual representation of of these data is not sufficient to actually make a conclusion or inferences. So we have to start thinking about how to model these data, because without computational predictive modeling, we will be only doing inferences that are very, very impoverished. I'm going to skip this slide. Building computational models requires very frequently to go incorporate everything from molecular biology to socialization. And of course, depending on the question, you don't need to incorporate all of them, but this is the general approach, that if you want to detect a disease, you might have to recognize it by looking at behaviors first, then perhaps cardiovascular system or neurophysiology for the person, and molecular biology. Now, this multi-scale modeling is handled by Grace Pang at NIH, NIBIB, and if you're interested in it, you should get in touch with that. She's running this very, very good group. Now, making these computational models is fine, but actually making them useful for a point-of-care decisions requires that you model individual, and in particular, me. You need to build models that would be available for the clinicians to be used in routine point of care in making diagnostic as well as therapeutic decisions. And this is the vision of the future that enables us to combine all the data into the decisions. Now, I'm going to talk a little bit about the different models. And in addition to grain of level of modeling, there is also the issue of how much data-driven models are. There are some models are purely data-driven and statistical, and others have almost completely based on physics and physiology knowledge of the problem. And I'm going to go through some of these quite quickly. I don't know how much time do I have because about 12 minutes or something like that? Okay. So a model that are completely statistical are like regression models, and I'm not going to spend much time, except that if you want to combine it with individuals, you have to use mixed models, and that's an interesting modification of models. Now, functional equations is something that you might not be familiar with, although parts of them you are. So for example, a functional equation is of the form of homogeneity. If a system is homogeneous, it's a hugely restrictive condition, and it will enable you to use data much more powerfully. Same thing is with Cauchy equation, which is the additivity. And when you combine them, you have linearity. By the way, we can almost derive the homogeneity from this equation. We might want to think about why do we need homogeneity in definition of linearity, but I'm not going to go into that. And another example of this kind of equation, functional equation, is scale invariance. If you have a recognizer that discriminates between x and y, for example, lengthwise, if you then multiply each of the components by lambda, the discrimination doesn't change. This is scale invariance. It means that if you have a closer picture or further picture of it will not change the discriminability. This is a very important scale invariance equation that allows you to then generalize to and constrain the models that you have. And that is equivalent to Weber's law, and I, again, don't have time to tell you about that. Body mass index is an interesting example of special homogeneity that has lambda square multiplying height, while lambda multiplies weight. And this was empirically observed, assuming that there is a health status that is invariant with respect to this homogeneity. Okay? But more recently, the quality of health has been defined in terms of body fat. And so the question is, does BMI predicts body fat? and it doesn't quite do a good job. And you can see that in these graphs, the BMI is on the horizontal axis, the body fat is on the vertical axis. There's lots of variability, so that BMI of 20 to 35 may be way below the obesity line that's specified by the World Health Organization. Speed of walking is a very important indicator of how well we do cognitively. So this graph shows time to walk 30 feet as a function of years. Here in the middle, at 0, a person is diagnosed with mild cognitive impairment. And you can see that several years before that, like 4 or 5 years before, there is already indicated that there is going to be a problem. If we were able to detect that change point over here, we would be able to anticipate mild cognitive impairment and intervene in helping people stay more active cognitively. Now, not only the average or median, but the variability increases, and that's a huge component that you'll see. Now, we measure speed of walking unobtrusively by looking at these sensors firing, and then we compute the velocity. But even for that, you actually have to incorporate the sensor models, and in particular because the triggering has errors both in time and space. And this is a graph that was computed by Daniel Austin, a student at OHSU. It shows a particular person over several years declining in their speed of walking. And here at this point, this subject was diagnosed with mild cognitive impairment. Another subject, this one has pretty constant speed of walking, but over here, this was a stroke. To be able to measure these things is very important, because maybe there was an indication in here that would give us some insight about what's going on with that person before actually ended up with stroke. Now, since variability is so important, we're wondering if you can predict variability from step to step, to variability to walk. And it turns out that for this subject, you can do a very nice job. For other subjects, not so good. So here are some correlations between the measurements that we would predict from step-by-step variability to walk-by-walk variability. I'm going to go fast through this, except that we need to connect the speed of walking and gait parameters with cognitive function. And we need to do that by actually building a model of how a person generates the gait parameters in order to perform the walk. And from that, we can then infer cognitive state. And let me give you a little bit of example. When you decide on how to walk, you have a choice of step size, cadence, and velocity. Now, currently, the notion in the field is that the choices are made to minimize energy for the stroke. But when you look at old people and they walk like this, like my father, it's not minimizing energy. It's clearly other aspects. And so we try to look into that. And in fact, it turns out that being out of balance is a very high criterion, and not being able to go fast enough. So we created an objective function that incorporates these, and using this objective function, we actually are much better fitting people who are elders and people with neurological diseases. So this is one way to incorporate cognition into knowing how gait. I'm going to skip sparse sampling a little bit, except that to tell you that using the data from the sensors in conjunction with something like semi-Markov models gives us a real powerful tool to look at activity. And the sparse sampling in this case is actually very useful because it enables us to get over the computational complexity that's usually associated with semi-Markov models. And at the end, I'd like to tell you a little bit about what we are just thinking about right now in trying to characterize activities. Well, the activities that I talked about are essentially firings of the individual sensors. It can be interpreted as sequence of events. Here you have bedroom, bathroom, walk-in closet, hall, living room, etc. Now, one can look at for recurring sequences because they will represent activities that people are doing in their homes. And then once you do that, then you can use something like Kolmogorov complexity to actually estimate how these sequences repeat over time. And in fact, we can assess the complexity in terms of compression, and that's a standard approach. And what we did was actually use Lempel-Ziff modified to be actually closer to Kolmogorov complexity than Lempel-Ziff usually is, to actually look at how people's activities change over time. And this is an example of a graph of a person in their home, monitored over a year or so, actually 2 or 3 years. And you see that at the end, this person is not well, is getting distant. Something is changing in their lives. We can now go in and figure out what it is that's changing in their lives. The other corollary of this is looking at the entropy, where we measure the number of bits that are required to characterize the activities of people as a function of time, and that is also going to be useful in predicting. So, the take-home message for this, from this talk is that healthcare needs to be changed, and that technology will play an important role, but that we need to address these issues by using as much technology as we can to enable information and assessment to be used in decision-making in healthcare. The focus is on key important healthcare problems. We need to understand how big data can be used in point of care, and I would argue that the only way to do that is use computational modeling more effectively. And I will end on that and ask you for questions. Thank you for your attention.
Thank you. Any question or comment from the floor?
It's late. Okay.
So you already said for big data you must need to some kind of modeling, but how large data we need to model?
So eventually, we will be able to take data from all electronic health records around the world to make the decision, to make optimal point-of-care decisions, right? Currently, we don't have that. Eric Topol already mentioned that in Patient Like Me and other social media, people are already beginning to do this kind of stuff, not with electronic health record, but with their own records. So these are going to be huge data sources in petabytes eventually. So we need a lot of technology to be able to do that. But even in the current environment, just the data from genomics, data from the kind of data that we have on behavior are actually huge, and we can't process it the same way we do have been working with laboratory data. Yeah, there's a question.
You talked about the interoperability of EHR, EMR systems, maybe on a global basis, which is pretty aggressive.
Yeah, can you use the microphone,
Is there a
please?
microphone? Oh, yes.
Thanks.
So the interoperability of EHR systems, what role would, or what infrastructure would allow that interoperability? For example, ICD-9 or now ICD-10, how do they play a role in this in terms of achieving the goals you discussed?
So, you know, the standards are, of course, useful. And the problem is that even within standards, right, you will find that individual organizations code their information differently. And at least the opinion of people who are much smarter than I am and more informed about this feel that the only way to achieve that is to build wrappers and develop a universal exchange language. At least that's what the PCAST reports were suggesting to overcome these issues. And it's going to be a huge problem. However, there's already a lot of effort on the way because of the fact that we have the meaningful use in place, and because actually the Department of Defense and the VA system are already beginning to trial, figure out how to work this out. So.
Paolo Bonato from Harvard Medical School. Thank you so much for the great talk. I really like the fact that you touch upon the difficulties encountered in affecting people's behavior. And I was wondering if you could comment upon the two alternatives that this technology might provide us with. One is to focus on preventive medicine and or secondary prevention, and therefore emphasis on changing people's behavior, versus focusing on the acute or chronic conditions and sort of end-of-life type of monitoring technology.
So this is a very important issue. Changing behavior is difficult, right? And I made that point several times. But there are beginning to be approaches that use technology to help us to do that. And again, I will push modeling as an important step in enabling that kind of intervention. The idea here is that if you understand what makes it possible for people to change behaviors, if you have then technology that can intervene in time, just in time, that can sense the potential of behaviors that are not warranted or they are not wanted, and intervene at the time, together with coaching that could be made economically feasible using technology, I think we will have some chance of making inroads into the behavioral change. And now, for the chronic diseases, it's a similar issue. The jury is out about how much, say, cognitive training is really helping. But the little data that we have seems to indicate that if we can help people to be cognitively engaged, socially engaged, and feel activated, actualized, that we will be able to make the end of life much higher quality. Paul.
Thanks for the talk, Misha. I mean, one of the take-home messages that struck me was that we live in interesting times. We have all of this data that can potentially make an impact on healthcare. I just wonder, based on some of the models that you showed, that essentially these models have been around for decades, and to try to get your input or what you thought about do we actually have the modeling capability yet to deal with this data, or is a fundamental thing that needs to be addressed are new models to be able to take advantage of this data deluge?
So I think it's both of those are true. First of all, although some of the models have been around, the data were not, right? It's only recently, and I think that Orcatech, the Oregon Health and Science University, is one of the biggest sets of unobtrusively monitored people for 4 or 5 years. So this is the first time we actually are exposed to see what's happening in people's lives and begin to sharpen our algorithms. But by the same token, since we are trying to infer activities, I don't think we are there with models. I think there is going to be a huge development in the area of modeling, and that would enable us to take the big data, but also the underlying processes that we are trying to model. So, for example, I mentioned the relationship between gait and cognition. We know it's there, but I don't think we understand what it is. By understanding the relationship, we might be able to actually intervene both ways. And so that will require modeling effort that's new. And the last thing I wanted to mention again is the behavior change. Models about how to change behaviors have been around, but they are more qualitative at the moment. We need to make them quantitative in order to optimize the intervention. And it's going to be a tough job. Psychologists have been trying for years and haven't been able to do that.
Yes, hi. I thoroughly enjoyed your thoughtful comments, and in particular, of course, the emphasis you place on modeling with respect to the healthcare system of the future. My question, which is also a comment, is I would like to invite your thoughts on the following, what I consider to be an apparent paradox, and concerns the issue of disruptive innovation. It is somewhat paradoxical to expect to have essentially sponsoring, meaning funding, of disruptive innovation by a system which is the peer review system, which is intrinsically and fundamentally non-disruptive. By its nature, and for good reason, the peer review system is rather conservative, it is incremental, and certainly non-disruptive. It's very much establishment-oriented. I have no personal complaints against it. However, I want to point out as a thinking person, and because I also respect your intellect from your comments, I would like to see how you view this issue, which is really a fundamental paradox that is not addressed as far as I know. People talk about disruptive innovation, but they overlook the fact that that cannot be sponsored or funded or supported by a process that's fundamentally non-disruptive.
Excellent point. I think it's the same question that I asked William Brody yesterday, right? It's a huge problem for us, but I think that we can help it at least a little bit by keeping very conscious about what our biases are in terms of the expertise. And when I run a panel, I ask continuously for the panelists to see, well, what is the disruptive here? What is the transformative idea here? And I think that forces people to think about. The other approach that I've discovered accidentally is that if you give people to criticize something and they are not materially involved, that they could benefit if they keep the idea to themselves, the group can actually create many ideas. And every once in a while I have to tell my panelists that they are judging the proposal at hand, not their idea of how that could be. And that kind of approach, may help us a little bit. But, this is one of those philosophical problems, like induction, that's not provable. And if anybody has ideas about how we can improve our approach to that, I would be very happy. NSF is continuously trying to bring innovation, and one into forefront. And one approach is to use multidisciplinary things, because when you bring one idea from another discipline, that often leads to something that's new. So that helps a little bit. But again, I don't have the answer. I would like to have it.
Yes, Nikos Maglaveras from the Aristotle University in Thessaloniki.
Hi.
Hello, Misha. The basic problem I see we have, let me just lay out just some thoughts, and I would like your comment. We have the big data versus the data of one person, okay? So in essence, we have, on the one hand, a lot of, let's say, data. And if we take, you know, the, let's say, central value theorem or whatever it is, then the mean would mean that, okay, we know what's happening, but this is not, of course, the case. It was very evident in the BMI that, let's say, you showed there. So I think that we have to find a way to really merge, on the one hand, the big data output and the personal data that are coming from the modeling, okay, and the, I would say, the combination of, on the one hand, of modeling each person as it concerns the physiological function, okay, like the virtual physiological human or whatever it is, and the p-health, and of course the social environment somebody is in. And the second problem I have in general, to be honest, after so many years in telehealth, is that the quality of data is very inhomogeneous across the different layers of the healthcare system. If we have integrated care, okay, we have home care and ambience in general, primary care, secondary care, the quality of data is very, very different. And in fact, in the home care and in the ambience in general, still I think we have to find about artifacts and noise that I say we are not aware of. So I think that, in my view, should be a priority.
So as I told you, I had to take lots of slides out of my talk to fit it. And one of them was exactly the issue of big data, small data. Because for one person, we may have too little data, even though we're facing huge data from the other side. Now, there is another problem that's currently very closely related to that. Usually you go to a doctor when you feel bad, when you're sick. And usually you have to be pretty sick to go to the doctor because it's such a hassle. Well, so the doctor never seen you healthy. They don't know what you look like healthy. And that's a huge problem. We hope that by using monitoring, unobtrusive monitoring, throughout lifetime, we would be able to at least establish some baseline for an individual that would give us some input into the modeling of the individual. But this is definitely one of the key issues in what needs to be solved in the new algorithms and new approaches to data analysis. There is a possibility, and this is one of the goals that people hope for, is that if you find patients like you, if you can match characteristics of you, that you could be using the subgroup of patients or people that are out there in the among the billions of people on Earth, that would match you and use that as a proxy for your own data. So that's one thing. The quality of data is a huge problem. In fact, most of our research time is being spent on making sure that the data are good, and that the heterogeneity data is another problem. And the only way to solve that is to develop algorithms that can, as well as possible, harmonize data across different data sources. And it's not going to be easy, but hopefully, to the extent that the data will contain common elements, we can do that. But it's up one of the problems that have been identified by the Presidential Council of Advisors and others. I think we need to end up there.
Yeah, okay, thank you very much. And so maybe continue to discuss in the next EMBC conference in Osaka. Okay, thank you very much, Paul.